identity. Now, no matter what is G1 and G2, it is phi of G1 by phi of G2 because it's a homomorphism, right? Now I can recall phi of G1 was identity because it was in the kernel. Phi of G2 is identity because it's in the kernel. So I have identity multiply identity. So it's identity. So product of two elements in the kernel is in the kernel. And the same story, since phi of G inverse is phi of G inverted, no matter what is G. If phi of G is identity, then phi of G inverse is identity. That's it. Okay. Well, this is not just any subgroup, it has some additional property. And this additional property is the following. If H is in the kernel, and G is any element of my group, then G inverse is in the kernel. It's kind of a strange, sort of a new absorption property. You remember, ideal has some strange properties.
Where'd H come from?
H is from the kernel.
Oh.
Not from group H, I'm sorry. You don't want me to use H?
No, that's fine. The kernel.
And G is any element.
Okay.
Then this contraption is also in the kernel. And how you're checking it, the only way to do it is through definition. So what I'm saying in effect, that this is identity, or this identity is in group H. And somehow it should be deducible from the fact that H is in the kernel and that this is a homomorphism. And of course you can write it, no matter what is G and H, you can write it like this. Well, I don't know, like inverse sign. Here you remember it. So that's no matter what. But now if you recall that phi of H is identity, then you're done. Because now this is identity, so it collapses, and then this product is identity. What?
Phi is a homomorphism from G to H, right?
Phi was a homomorphism from G to something.
Okay.
And then I had a kernel of it.
Yeah.
And I had an element in the kernel.
Yep.
Then this operation is called conjugation. Conjugation of element from the kernel is also in the kernel. The reason is this simple computation. Okay? So it tells me that not any subgroup can be a kernel, but only subgroup with this additional property. Maybe there are some other properties, I don't know yet. But this property should be for sure satisfied if I want subgroup to be a kernel of homomorphism. Okay?
If this is satisfied, is it definitely a kernel?
It turns out that yes. That if it is satisfied, it certainly can be, we can manufacture a homomorphism for which it will be a kernel. But we'll do it later, okay? So there is one other proposition, and namely if we have two numbers, that looks familiar, but from our previous line. If we have two numbers which are relatively prime, don't you remember? We had a lot of questions like this. So if m and n are integers such that they are relatively prime, then Zmn is isomorphic to Zm cross Zm. So what is written here? So this is some data about these numbers. This is group of these under addition. We don't have group under multiplication here. Remember, it's a ring. But under addition, it's a group. Do you remember we discussed with you last time this construction? Yeah. Claim is that these two objects are isomorphic, provided n and m are relatively prime. By the way, if and only if they are not relatively prime, it's not true. So is it if and only if in your book?
No.
Just, but it goes both ways. Yeah. Goes both ways. I'm unable to do it. Okay. So, left side is pretty simple-minded group. It's a cyclic group of order Mn. Agreed? It has element 1 which generates it. So if we want to show that this is true under this condition, we somehow should find an element here of the same order, of order Mn. And you know which element it will be? Any takers? Remember, this element is a pair.
M comma N?
Very bad. M is 0. Yeah, N is 0. So what you're suggesting to me, 0, 0, which is identity element. Try to do better than that. Yes, 1, 1. It's easy to check that under this condition, this element has order Mn. Okay. Now, certainly, if I take this element and raise it into power Mn, it will be identity, right? Because what is raising it into power? Operation here is addition. So it is Mn, comma Mn, right? Raise it into power means in this context add it to itself this many times. It's just for equal. So you will, okay. You understand? Okay. And of course this is 0 because this is divisible by n, and this is 0 because it's divisible by n. Okay. So now I want I want smallest number. It doesn't tell me that it's the order, right? I want smallest number. So 1, 1 in power d is dd. Right? And if it's order, then it's the same as 0, 0, right? Because that's my identity element. Right? So because of that, M must divide D to make it 0.
And N
must divide D to make it 0. Since M and N are relatively prime, it means the product divides D. That's it. And the same proof goes if they are not relatively prime. Because if they are not relatively prime, then certainly this element does not have order Mn. It has smaller order. It has least common multiple order. Of course, it's proof for this element, but then it's very easy to prove for any pair that least common multiple would be its order. Let me stay correct. That any element raised into power least common multiple give us neutral element. For this it will be exact order, for others maybe it will be dividing it, but I won't have an element of order Mn, if M and N are not relatively prime. Okay. So for example, Z6 is isomorphic to Z2 cross Z3. And pushing it to the extreme if you have primary decomposition of M, right? If N is P1 in power A1 by P2 in power A2 and so on, where these are different primes, then Zn is isomorphic to Z P1 in power A1 cross P2 in power A2 and so on, right? Cross K in power A, right? How you will prove it? You will present it as product like this, right? These are two relatively prime numbers, so you will chip this away, multiply something. This something has this many elements, and then you chip it. Okay. So in a sense,
No.
yeah, in a sense, that's kind of interesting presentation. One of the ways to prove Euler formula is through this presentation. You remember Euler formula? How many numbers relatively prime to n are before n, right? Okay. Okay, so we're done with you with isomorphisms. Oh, well, I'm done with isomorphisms. Next section is cyclic groups.
We're skipping that one, right? I thought we were skipping that one. I'm just kidding. I'm sorry.
I think you had a question about this.
Oh, you know what? You can stop me. You have some questions. Ask me, because otherwise I will cover next section.
Please ask questions.
Oh, wow. It's going to take a second to think of it again.
You know, it will be a good policy to write it on a piece of paper.
I wrote it on a piece of paper in my head, and then I forgot.
Piece of paper in
I said, oh, I'll think of it so quickly, it's fine. Oh, it's about, it's, yeah, like example 2.3.3, page 74.
That's 70.
Page 74. I think this is a pretty simple question. I just thought of it as I was trying to read through this, and so I wanted to ask you. I almost called you.
Page 74?
Yes.
Which example?
The very bottom, 2.3.3.
We have a permutation in S5, and it's a cycle of length 3 written, okay. And it's not a cycle since whatever. So, what's the question?
My question is, so if you show that a permutation can be written as a product of two cycles, does that imply that the permutation was not a cycle? Because that's what this is.
Yeah, it's just definition. Permutation is called a cycle if it's just one cycle.
Oh, so
It's not something to be, to prove or to be excited. It's just definition.
So if you have two cycles, it can't be called a cycle?
Yeah.
It's called a product of two cycles?
Yeah,
Oh, okay.
Of course, you have to take care that these are commuting cycles on different elements.
Huh? What?
That it is cycles on different elements. 1, 3, 4
Are
is
you
one
saying
cycle.
are you saying disjoint? Are you saying disjoint or?
Yes,
Okay.
yes. Yeah. Because otherwise, it may be just stupid way to write a cycle as product of two cycles which overlap.
Right.
Then it's not legit. So what is legit? If you take any permutation,
Yes.
you can write it as product of disjoint cycles.
Okay.
Given. Okay? Understood. Permutation is called cycle if this consists of one cycle of length more than 1 and all other cycles are of length 1.
Oh,
That's it.
right, okay.
Okay. It's just definition. Just a name. Did you have another question? It didn't work too well because, I can go back to cycle groups.
I'm sure someone else has something.
Could you just do, like an example of,
Sure.
like a composition of like two cycles that
Overlap?
overlap?
Oh, sure,
Because I don't know, like I always want to read it like left to right, but I know you have to go right to left.
I know.
And I feel like I'm being
This
dumb,
one.
but that's the way I read it.
1, 2, 1, 3.
All they have to do is have one number in common, right?
So
And
those
they,
Then they overlap, yeah.
One,
It's enough to have 1, 2, 1, 3. And say we have, how many elements you want in the set? Just 3?
Yeah.
Okay. So then what we have to write? Now we want to figure out where 1 goes. Where 1 goes? 1 goes to 3. And
3.
That's it. So 1 goes to 3. Where 3 goes? 3 goes to 1. 1 goes to 2. Where 2 goes? To 1. That's exactly the situation when you have 2 overlapping cycles.
The guide for this online actually said that other books, if you're studying multiple books, some other books will say read left to right.
Yeah, that's
What?
interesting, yeah.
Yeah,
Wait,
but because I read on the they'll tell you on the online guide that other books, if you're studying multiple books, they'll tell you to actually read them left to right, but they want you to keep in the framework of looking at like it's a composition of functions, how we always read inside out,
okay.
with functions.
Yeah. So, we just have to be consistent. That's the only. You shouldn't switch from, one to
one
one.
to the other.
There was
But
a,
is it clear? What we did, and that's how you are doing it. No matter what you have, you have, I don't know, 1, 2, 3, 3, 4, 5, 6, 5, 7. Say product like this. How to go? Well, big deal. Take 1, goes to 2. Is it clear? Take 2, goes to 3. Right? Take 3. Oh, goes to 4, stays in 4. Okay? Take 4. Goes to 5, nothing. Take 6. Oh, goes to 5. 5 goes to 3.
3, which 3 goes to 1.
3 goes to 1. Oh. Cycle. Okay. 1, 2, 3, 4, 5. Oh, well, I still have 6 and 7 to look at. 6 goes to 7. Right?
You already used.
No. 6, why am I saying 6 goes to 7?
Yeah, so
Something's
5
wrong.
should take us to
6 goes to 5.
5 takes us to 3.
5 goes to 3.
1 takes us to 2. Well, 3 will
3
take
goes
us
to 1.
3 will take us to 1.
Something is wrong
And
here.
then 1 will take us.
I'm making some mistakes and
3
you're
goes
not
to
helping.
1.
Was this correct at least 1, 2, 3, 4, 5?
I don't know.
I don't understand the 5.
Okay, let's look again. How about 1? 1 goes to 2 and that's it, right? 2 goes to 3 and that's it because that was before. Now 3, what happens with 3? Goes to 4, right? No 4 here, so that's fine. What about 5?
5 goes to 3, 3 goes to 1.
3 goes to 1.
So you need a 1 there. After the,
5 goes to 3,
Oh, wait,
3
no.
goes to 1, so 5 goes to 1.
okay.
Right?
Okay.
Okay, well, at least this is correct.
It might just because you have 5, you have 6, 5 maybe.
So 5
Goes
goes,
to 5.
that part is correct.
Yeah.
Okay, let's do with 6.
6 goes to 1.
Cannot be. Something is wrong there.
Why? It cannot be.
Because 5 goes to 1.
So does 6.
It goes to,
Permutation, bijection.
it goes to 3.
6 goes to 5. 5 goes to 3. 3 goes to 1.
You have 5 both going to 3 and a 7.
That's right.
That's where your problem is. Because in this last part here, 5 will take you to 7, but in the middle,
I think if you flip.
5 will take us to 3.
Something
Like
is wrong
5
here.
and 6, I think you'd be right.
Something is wrong here. So what's the big deal? So 5 goes to 7.
But 5 can't go to 7 and 5 can't also take you to 3, which
5
is
can
1.
go to wherever it lies. I have 3 different permutations, a composition of 3 different bijections.
So 5 will take us to 1 and to 7.
No. In this composition, 5 will go us to 7.
Yes.
In this composition, 5 goes to 3. In this composition, 5 stays put. I have 3 sorry, I was using words wrong. I have 3 bijections. This bijection permutes these guys, everything else stays put. This bijection permutes these guys, everything stays put. This bijection permutes these 3 guys, everything stays put. Right? I have composition of these 3 bijections. Composition of bijections must be a bijection. Right? So it cannot be that.
Oh, well, 7, we were supposed to look at the far right first, so 5 should just go to 7, 5 doesn't take us to 1.
So maybe that's something is wrong here. Well, help me to find mistake. No? So where 5 is going? Okay.
5
where
takes the 7,
So it's not going to 1.
not going to 1.
Ah, okay. Well, so that was it. No?
Oh, yeah,
Okay?
you're right.
Yeah,
Yeah.
good.
This was the,
That's
yeah.
how we're supposed to
Five
start.
goes
Yeah,
to 7.
you know, because I was not looking at this, I looked immediately at this.
Yeah, actually, part of the problem I think was that your process started as like when you looked at 1, 2, and 3, you started looking left because you knew they weren't over there on the right.
Whatever is
got in
my
that
problem.
habit.
You know, I know better what's my problem.
I know.
My problem is you. Okay, I mean not.
As a
because-
teacher, actually
Okay.
that is.
So 5 goes to 7, right?
Yeah.
And 7 stays put. Oh, okay, 7. Okay. Well, where 7 goes?
To
6.
To 6, and then stays put.
That's
Okay, where 6 goes? 5. 6 goes to 5. 5 goes to 3.
3 goes to 1.
So now this is a cycle. Maybe this is better.
Looks a lot better.
And we're done.
We're done. All 7 elements are there.
Right. And if there's more elements, they just are. What are those ones called?
What?
What are those ones called? Identities?
Transpositions. What? Which switch only to
No, I was just thinking like, let's say that set actually had 8 elements in it. We could just write an 8 there, but it's just the identity.
Okay, you're not. You're omitting.
8 is the identity.
Singletons, you're always omitting.
Singletons are always identity.
Yeah,
Right.
you're don't write them. Cycles of size 1 just omitted.
Right.
You know, it's just agreement. Convention is that they're omitted, so If we have 10 elements, it means that 8, 9, and 10 are the same.
Okay.
So you see I have three cycles, and their product is 1 7th cycle. Okay. Okay. Yes.
I did have another question, page 81.
Page 81.
The proposition 2.3.10.
Any permutation in a Sn where n is larger than 2 can be written as a product of transpositions.
Who's this?
Let's repeat it. Okay, let's repeat it. Or did you discuss it? And he understood it? No?
I think you'll remember it.
Okay. Well, one thing you already agree. It's always can be written as non-overlapping cycles. Right?
What then?
Any transposition. Any permutation, I'm sorry, any permutation can be written as a product of non-overlapping cycles.
Disjoint.
Disjoint cycles.
Cycles.
Oh, okay, disjoint cycles. So we will be done if we just take one disjoint cycle and manage to write it as product of transpositions.
Okay.
Agreed?
Yeah.
Okay. So let's take a cycle of size n, and since that's just up to us, our numeration.
It seems pretty simple. It's just the notation that they use. Before they talk about the alternate notation, the first one, I don't get it.
So I take n cycles. Do you want me to start with example where n is some particular number? I see, yes. Okay, 1, 2, 3 is the first interesting example. Right? Because 1, 2 is already transposition. So how to write 1, 2, so where 1 wants to go?
Oh, use reverse cycle. Is that what we're talking about?
1 goes to 2, right?
Yeah, one goes to 2.
So let's write 1, 2. It's certainly not correct equality, I have to proceed. So where 2 wants to go? 3. To 3. And what 2 is doing? What 2 is doing? 2 is going to 1. And I want 2 to go to 3.
So one goes to 3.
Let's write 1, 3. Okay, now 2 also went to right place, right? 1 went to 2, and that's the end of the story. Right? And now 2 went to 1, and 1 went to 3. Well, where 3 goes with this product?
Back to 1 where it should.
That's it. Okay? Well, I'll do one more. Let's do this with 5, okay? And you understand that any 5 cycle, they're all created equal, so...
Still not the same as the notation they have.
Look, notation.
What page are you looking at?
81.
Where 1 wants to go? To 2. Where 2 wants to go? To 3 and goes to 1. Okay, so now both 1 and 2 are going where they should, right? 1 goes to 2 and 2 goes to 3. Okay. Where 3 wants to go?
4.
Okay. You got the drift. So let's check that it works. So 1 goes to 2 and there is no 2 any further, so it stays put. 2 goes to 1 and then goes to 3 and then stays put.
Yeah.
What happens with 3? 3 goes to 1 and then goes to 4 and then stays put. What happens with 4? Goes to 1 and then goes to 5. And that's where 5 goes? To 1.
Okay. In their notation, in here, the way they have it written out, is that the element on the right of every transposition is a sub r, like in this case, 5. Can you write it like that?
Okay. You see, I was doing everything through element, through the first position. They're doing everything through the last position.
Okay.
You have many ways to skin the cat. What's your problem?
There's 5 different ways to write all that.
Huh?
You start with 5.
Okay.
5 goes to 1.
Yeah.
Right?
Sure.
That's what is written there?
Yeah.
Now,
Yeah.
if we start with 5 and 5 goes to 1, then we can discuss 4. Where 4 goes?
To 5.
Okay. 4 goes to 5. It's more convenient to do it like this.
No, I want to see how this, please.
It's gonna be 2, 5,
Yeah, it should be 2, 5.
and then 3, 5. And then 4.
3, 5,
So like you're
And
you're
4,
looping
5,
5
right?
instead of 1.
Oh, let's just carry it out.
Okay, so that's what they're suggesting,
Yeah.
right? So where 5 goes
So,
and stays put. Where 2 goes?
To 5, and it goes to 3.
5 to 3.
Okay.
And then 3.
Where 3 goes?
Wait,
And 5 goes.
sorry, where's 2 go?
2 to 5
Yeah.
and then to 3.
So
And then you're
And
done.
then
Okay, good.
Where 3 goes?
To 5 and 4.
And then to 4. And where 4 goes?
To 5.
That's it.
Okay, alright. And
So
this is
it
what
doesn't matter, you can do it this way, you can, of course,
we were talking about this not being unique, but there's always gonna be an even number.
okay, yeah.
Right.
Well, in this presentation, actually, you have 1 unit less than, so if it's size 5, you have 4 permutations.
Oh, if you use this,
Yeah, if you
Formula,
use
so to
this
speak.
particular,
right,
approach.
this process, okay.
Yeah, so it's interesting because this is 3 cycle.
Yeah,
3 is an odd number, right?
yeah,
But this is even permutation. Because it's composition of 2 transpositions.
okay.
And this is 5 cycle, again odd number. And it's again even permutation, because it's composition.
Always the case?
It's always the case. Odd size cycle is even permutation.
Okay.
Because it's always composition of.
Do you remember the guide that has the extra problems and stuff on it? If you go to the solutions, there's a see more thing I noticed and clicked, and all of this is actually pretty well explained. It was really nice.
Okay.
There's some things I think you really might find interesting in there for that section.
Alright, thanks.
Okay, we have time for one more question.
Something from groups, somebody.
I don't even know how to ask
From
questions
3-1.
in groups yet. I don't know what would be beneficial for them.
Okay, so what I suggest, when you're seeing something, write it not only in your head, but also on a piece of paper.
I thought of that question quick though, huh?
Yeah, it was brilliant. Okay, have a good weekend, spend some time learning mathematics. Otherwise, goodbye.